Hello and welcome. Today, we're diving into the world of large language models, or LLMs. These AI powerhouses are behind many amazing applications, but running them can be incredibly demanding on computers, making them expensive and sometimes slow. To use them effectively in the real world, we need to optimize them for inference. That's the process of getting an output from a trained model. The goal is simple: make them faster and cheaper to run without losing too much of their capability. So, how do we do that? One popular set of techniques falls under model compression. Think of it like making a highly detailed digital photo smaller so it loads faster and takes up less space. First up is quantization. This is a very common method. Models usually store their internal numbers, their weights, with high precision, like 32-bit or 16-bit floating point numbers. Quantization lowers this precision, often down to 8-bit or even 4-bit integers. Just going from 16-bit floats to 8-bit integers can halve the model's size. This means it needs less memory, can fit on less powerful hardware, and calculations often run faster, sometimes 2 to 4 times faster. While reducing precision too much can hurt performance, 8-bit and 4-bit quantization often work surprisingly well with minimal accuracy loss. This can be done after a model is trained, which is called post-training quantization, or even incorporated during the training itself. Next, we have pruning. Imagine carefully trimming unnecessary branches from a plant to help it grow better. Pruning does something similar for neural networks. It identifies and removes weights, or even entire components like neurons or attention heads that aren't crucial. This creates a smaller, sparser model that needs less computational power and memory. It can significantly reduce model size, but it's sometimes tricky to get right and might require some retraining or fine-tuning to regain any lost performance. Then there's knowledge distillation. Here, we train a smaller, compact student model to mimic the behavior of a large, powerful teacher model. The student learns from the teacher's outputs and aims to capture its knowledge in a much more efficient form. This can lead to student models that are dramatically smaller and faster, while still performing almost as well as the original large model. Beyond compressing the model itself, we can optimize its architecture, particularly the attention mechanism, which is often a performance bottleneck. Techniques like flash attention optimize how attention calculations use memory, speeding things up. Paged attention cleverly manages the memory used to store intermediate results, called the KV cache, preventing waste and allowing models to handle longer inputs. Other architectural tweaks like multi-query or grouped query attention reduce the size of this cache significantly. Optimizing the inference process itself is also key. We already mentioned the KV cache. Storing these intermediate key and value results is crucial because it avoids recalculating them for every new word generated, speeding things up massively after processing the initial prompt. Efficiently managing this cache is vital. Batching is another crucial strategy. Instead of processing one user request at a time, servers group multiple requests together. This keeps the processors, like GPUs, busy and increases overall efficiency. Continuous batching is particularly effective for live services, dynamically adding new requests to the queue to minimize idle time and latency. There is also a clever trick called speculative decoding. It uses a smaller, faster draft model to predict a few words ahead. The main, larger model then checks these predictions in parallel. If the draft model was right, the larger model can accept multiple words at once, significantly accelerating generation. Of course, using the right hardware, like powerful GPUs or specialized AI accelerators, is fundamental. And specialized software frameworks like VLLM or TensorRT bundle many of these optimizations, like paged attention, continuous batching, and quantization support, making it easier to deploy highly efficient models. In conclusion, optimizing LLM inference involves a mix of strategies, trading off speed, cost, memory, and accuracy. Quantization, pruning, distillation, attention improvements, smart caching, batching, and speculative decoding are all powerful tools. Often, the best results come from combining several of these techniques. As research continues in algorithms, software, and hardware, We can expect LLMs to become even faster and more accessible, powering even more applications in the future. Thanks for tuning in.